we're picking up with chemicals in cells. There are two categories of chemicals, organic and inorganic. What makes a chemical organic is not that it was grown without pesticides. In fact, a lot of the pesticides are chemically considered organic molecules. It means it has to be a molecule, so there are covalent bonds in it, and it contains both carbon and hydrogen. Inorganic is anything else. Most of the inorganic substances in the body are ions and some smaller molecules that don't qualify as organic. For example, water, it's a molecule, it has hydrogen but no carbon. Oxygen, it's a molecule, but it doesn't have hydrogen or carbon. Carbon dioxide, another molecule, has carbon but no hydrogen. And then the majority of electrolytes, like sodium and potassium ions, are inorganic. And that's all we're going to say about inorganic. The majority of this section looks at the major categories of organic molecules. Those are carbohydrates, lipids, proteins, and nucleic acids. 3 of those are on all your nutrition labels. Even if it's water that has nothing in it but water, it's a thing they have to list and say that it doesn't have any. But instead of lipids, it's written as fats. And nucleic acids, one of those is illustrated here. That's what the Na stands for in DNA. For each of these categories, we're going to look at what makes a molecule fit in that category, how we classify things within that category, and what we use them for in the body. So, carbohydrates contain carbon, hydrogen, and oxygen. And it's roughly a multiple of carbon plus water, although it's not arranged that way. So equal amounts of carbon and oxygen, and then twice as much hydrogen. In fact, that's where they get the name, carbohydrate. So a typical carbohydrate is C6H12O6, that's a lot of our sugars. Another example, C12H22O11. So the numbers aren't exact, but they're close in that case. Structurally, they often form a ring where your chain wraps up on itself, like this. So we can follow the carbons around like that, and then they put that extra link on it. The main use for carbohydrates in the body is as fuel. We burn them for energy. Carbohydrates are classified by size. Small ones, CHO is often used as an abbreviation for carbohydrate. Small ones, including monosaccharides and disaccharides, are also called sugars. Then the larger ones are polysaccharides. Saccharide part means sugar. Anyone know what mono is? One. Di? Two. Poly? Many. So our categories are 1, 2, and a lot. A monosaccharide has between 3 and 7 carbons. So your smallest monosaccharide has 3 carbons, an oxygen attached to each, and then anywhere else you need another bond, there's a hydrogen. Because of the way their electron shells are starting off, hydrogen can only make 1 bond. Oxygen makes 2, carbon makes 4. This is called glycerol. And it's too small to wrap up into a ring. But 5, 6, and 7 almost always wrap up into a ring. Disaccharide. So I have here two models of monosaccharides. This ose ending refers to sugars. So anything that's named ose, that's an odd location for it. Anything that's named ose is going to be a mono or disaccharide, or at least a carbohydrate. Yeah. Sometimes we'll give it a number ose for how many carbons are in it. So a pentose has 5 carbons, hexose has 6 carbons. Both of these examples are forming the ring, and you can see where each carbon has an oxygen attached to it. And one of those attached oxygens dropped its hydrogen and hooked onto another carbon to make that ring. So we'll pass these around for you to look at. When we make these models, black represents carbon, probably because of soot. Red represents oxygen, because oxygen makes our blood red. And then we use white for hydrogen, just because it's a convenient color when you're going to have a lot of it. So some examples of monosaccharides. Glucose is the most common sugar used in our bodies for fuel. Fructose is one found in a lot of foods. And ribose is going to be a building block for our nucleic acids. Questions on monosaccharides? To get a disaccharide, you hook 2 monosaccharides together. Here's our 2 6-sided sugars. So if you get this in front of you and fiddle around with it, you can find the 2 rings, one for each monosaccharide, and then here's the oxygen bridge holding them together. Our table sugar, sucrose, is a disaccharide. So is lactose, the sugar in milk. What makes them different is which monosaccharides are in them. Polysaccharides, I don't have a model for because we don't have that many of the little atom balls. We're talking dozens or even hundreds of monosaccharides linked together. There are some molecules that have like between 3 and 10 monosaccharides, but they're not very common. Polysaccharides are used to store carbohydrates when you don't want to burn them right away. When plants store them, we call it starch. In animals, we call it glycogen. We store glycogen in our livers and in muscles so that when they need energy, they can just break the glucose off the ends. We could use our pop beads to represent a polysaccharide, where each bead would be a glucose. Most of the time, polysaccharides are built out of just glucose. Another type of polysaccharide is used for structure, especially in plants. There's one called cellulose that is what makes your vegetables crunchy. It forms walls around the cells to give the plant more structure. We can't digest it, so we call it dietary fiber. Any other carbohydrate questions? Our next group is called lipids. Lipids also have carbon, hydrogen, and oxygen, but they generally have much, much less of the oxygen. Because oxygen is the one that makes polar bonds, That means there's very little polarity in a lipid. A typical lipid is a chain of carbons with a little bit of oxygen on one end. This one is what's called double bonded to the carbon, so it's not polar. This one has the hydrogen, so this is the one polar bond in the whole thing. All the rest of this is just carbon to hydrogen, and they're nonpolar. That means they're not soluble in water. The word for that is hydrophobic. What's a phobia? Fear. Yep. So we call them afraid of water because when you try to mix them together, they move away from the water. It's not that they're going, ew, water, I hate it. It's that they can't stick to it. And so the water sticks to itself and to anything else that can, and just kind of leaves the hydrophobic things off to the side. When something is soluble in water, we call it hydrophilic. Anyone know the root phil? It's used in Philadelphia, city of brotherly love. Phil is brotherly love. There's like 6 different words for love in Greek. And phil is like family and friends. So hydrophilic things love water. They meet water and they go, hey bro, how's it going? Let's hang out. Carbohydrates are hydrophilic. Lipids are hydrophobic, and that's their defining feature. The major types of lipids are fatty acids, which, like monosaccharides, are going to be used to build the other kinds, triglycerides, phospholipids, and steroids. A fatty acid is a chain of carbon with hydrogens bound along it. One end has this thing, which I drew up here. This is called a carboxyl group. So when you draw it out in the molecule, it looks like that. When you write it, it's often just said as COOH. Now, because that hydrogen is on the end stuck to an oxygen, it can be released. The polarity can be strong enough that the oxygen just takes the electrons and the hydrogen goes, okay, I'll see you later. That means you're putting hydrogen ions into solution. That's why we call it a fatty acid. Fatty acids can be burned as fuel and used to produce other lipids. So here's one example of a fatty acid. So the first thing you might notice looking at this is the red's all on one end. And then you've just got black and white, nonpolar. There's one thing different about this other one, which I'll explain coming up. Fatty acids can be classified as saturated and unsaturated. When you talk about a sponge being saturated, you mean it has sucked up all the water it possibly can. A saturated molecule has as much hydrogen as it possibly can, which means we've got our carbons in a chain, and where they're not holding on to each other, they're holding on to hydrogens. To have less hydrogens, you get what's called a double bond. It's kind of like carbon has 4 arms, and it has to be holding hands with somebody with every one of those arms. The double bond is they hold 2 sets of arms together, and then they each have one more arm for something else. If you were to separate that bond, then they could each have another hydrogen. So that's why we call it unsaturated. It could hold more hydrogen. Now, why saturated and unsaturated fatty acids matter is what kind you eat affects the types of cholesterol in your blood. And that can affect your risk of heart disease. fatty acids going around. One of them is saturated, the other one is monounsaturated. Okay. So the double bond with the oxygen isn't counted. You look for double bonds between the carbons. So the one that has none of them is the saturated. One that's going around has one, that's called monounsaturated. If it has more than one, it's called polyunsaturated. So this one has two double bonds in the carbon chain. Triglycerides are made of 3 fatty acids, but unlike the monosaccharides, they can't just attach to each other in a chain. They need something else holding them together. And that's